Section: Introduction. In this section, we discuss the emergence of large language models, LLMs, as a significant step towards artificial general intelligence, AGI, due to their abilities in reasoning, role-playing, and creative writing. However, traditional LLMs do not understand multiple types of data, leading to the development of multimodal LLMs, MLLMs, that can process images, audio, and other forms of data. These MLLMs often use external encoders, like EVA Clip or CLAP, along with alignment modules to integrate non-text data into the LLM's framework. We identify four main approaches for MLLMs. 1. Discrete in discrete out, DIDO, where non-text data is converted into discrete forms before being processed by LLMs. 2. Continuous in discrete out, CIDO, where LLMs take in continuous data and produce discrete outputs. 3. Continuous in continuous out, CICO, where LLMs handle both input and output as continuous data. 4. Autoregression plus diffusion, AR plus diff, which combines autoregressive and diffusion modeling. While these methods have advanced MLLMs, they still have limitations. For instance, some models focus on text, images, and videos but overlook speech, which is different from visual data. Others, like any GPT, attempt to include multiple modalities but lack capabilities in video and voice synthesis, limiting their overall performance. Moreover, many current MLLMs primarily focus on understanding rather than generating multimodal content. Some solutions, like Hugging GPT and GPT-4, use external tools for generation but are not fully integrated. The recent introduction of GPT-4o shows promise as it can process and generate multimodal tokens in a unified model, demonstrating strong capabilities in various tasks. To tackle these challenges, we present MIO, Multimodal Input and Output, the first open-source model that integrates understanding and generation across text, images, speech, and video, allowing for the creation of interleaved sequences. MIO uses discrete multimodal tokens to capture both high-level meanings and low-level features from raw data. This model treats non-text modalities as different languages, enabling it to be trained effectively. We implement a three-stage pre-training process followed by a fine-tuning stage to enhance the model's capabilities. Our results indicate that MIO performs competitively against existing dual-modal models and sets a new standard for interleaved video text generation and complex reasoning tasks. Section Summary. In this section, we discuss the evolution of large language models, LLMs, towards multimodal capabilities, highlighting the limitations of existing models and introducing MIO, our open-source any-to-any foundation model that integrates understanding and generation across text, image, speech, and video. MIO uniquely supports multimodal interleaved sequences and demonstrates competitive performance in multimodal tasks, addressing gaps in previous models while leveraging a three-stage training process. Section: Method. In this section, we outline our methodology. First, we discuss our modeling approach, which accommodates both multimodal token input and output, as well as causal language modeling. Next, we detail our three-stage pre-training process. Finally, we explain our extensive supervised fine-tuning across various multimodal understanding and generation tasks. Our framework, MIO, consists of three components: multimodal tokenization, causal multimodal modeling, and multimodal detokenization. For multimodal tokenization, we utilize seed tokenizer for images and speech tokenizer for speech. Seed tokenizer processes images using a vision transformer derived from BLIP2, converting the encoded features into fewer tokens with causal meaning through a Q-former. These features are then quantized into discrete tokens that align with the text space of our language model, with a total of 8,192 discrete image tokens. Each image is resized to a resolution of 224 by 224 pixels and represented by 32 tokens. We use special tokens, less than image greater than and less than image greater than, to mark the beginning and end of image tokens. For videos, We first cut them into image sequences, adjusting the number of frames based on the video's duration, context length, or scene changes. This helps us stay within the context window limit of the language model while capturing essential information. Each frame is tokenized like an image. For speech, Speech Tokenizer employs an 8-layer vector quantization method to create tokens from speech, using 8 codebooks. The first layer's output, derived from Hubert, captures more semantic information, allowing us to distinguish between content and timbre tokens. We encode speech at a rate of 50 tokens per second for each codebook, totaling 400 tokens per second. To enhance efficiency, we only use the content codebook and the first 3 timbre codebooks, resulting in a vocabulary size of 4096 for speech. Given the diverse voices in our training data, timbre tokens can be random and noisy, while content tokens are more consistent and aligned with transcriptions. We identify 4 codebooks: A for content tokens and B, C, and D for timbre tokens. We explore 2 interleaving patterns for token sequences, a sequential pattern and an alternating pattern. Our experiments show that the alternating pattern complicates text-to-speech training and slows down speech-to-text understanding due to the noise in timbre tokens. Therefore, we discard timbre tokens for understanding tasks and adopt the sequential pattern for generation tasks, using less than SPCH greater than and less than SPCH greater than to denote the start and end of speech token sequences. In causal multimodal modeling, we tokenize speech and images, including video frames, using our respective tokenizers. We expand the vocabulary of our language model to include 4096 speech tokens and 8192 image tokens, along with 4 new special tokens. This brings our total vocabulary to 12,292 tokens. The image tokens carry causal meaning due to the causal cue former, while the speech tokens are inherently causal because of their temporal nature. This allows us to treat multimodal tokens similarly to text tokens for autoregressive training, unifying our training objectives into next token prediction with cross-entropy loss. Our training objective involves predicting discrete multimodal tokens, with the model initialized using the pre-trained Yi6B base. To address computational inefficiencies from padding tokens, we implement a masked packing strategy, concatenating samples until the context window is full and applying a causal attention mask to isolate tokens from each sample. Section Summary. In this section, we outline our modeling approach that incorporates multimodal tokenization, causal multimodal modeling, and multimodal detokenization, utilizing seed tokenizer for images and speech tokenizer for speech. We detail our pre-training and fine-tuning processes, emphasizing the integration of diverse tokens into a unified language model framework to enhance multimodal understanding and generation tasks. Section: Multimodal detokenization. In this section, we discuss multimodal detokenization. After generating multimodal tokens, we need to use specific decoders for each type of data to reconstruct images or speech from these codes. For image tokens, we apply the seed tokenizer's decoder, which uses a multi-layer perceptron to transform discrete codes into dense representations. These representations then guide a standard diffusion model to create images in pixel format. For speech tokens, we generate timbre tokens using a non-autoregressive model outside the language model, and then we combine these with content tokens to synthesize speech using the speech tokenizer decoder. In our approach, we also generate timbre tokens through the autoregressive language model to integrate timbre information into the multimodal language model. Next, we outline our pre-training strategy, which consists of 3 stages, each with distinct goals. The first stage, alignment pre-training, aims to create a multimodal representation that aligns closely with text. We use 2 types of data: image-text paired data, which has strong dependencies between images and text, and image-text interleaved data, which is more natural but less aligned. We focus on the paired data in this stage to ensure a strong alignment. In the second stage, interleaved pre-training, we introduce image-text interleaved data, including video text data, to explore a new dependency pattern. This interleaving allows for context-aware image generation, where text provides context rather than a direct description of the image. This approach is crucial for tasks like visual storytelling, where images are generated based on context rather than detailed descriptions. We also reduce the use of image-text paired data to avoid overwhelming the model and increase the batch size for interleaved data, video data, and speech data. In the third stage, speech-enhanced pre-training, we address the imbalance in token generation between speech and images. Our speech tokenizer produces many more tokens per second of audio compared to the image tokenizer. To prevent the model from focusing too much on speech, we gradually increase the proportion of speech tokens across the stages, starting at 12.5% in Stage 1, moving to 37.5% in Stage 2, and reaching 75% in Stage 3. This careful adjustment ensures that the model maintains performance across all modalities while enhancing its speech capabilities. We also keep the data mixing ratio for other modalities minimal and focus on high-quality subsets. This stage requires fewer computational resources due to the groundwork laid in earlier stages. For more details on hyperparameters and prompt templates, we refer readers to the appendix. Section Summary. In this section, we describe our approach to multimodal detokenization, where we utilize modality-specific decoders to reconstruct images and speech from generated tokens, and outline a three-stage pre-training strategy that enhances multimodal representations by progressively integrating image text and speech data. Each stage targets specific objectives, such as aligning non-textual data with text, enriching contextual semantics, and optimizing speech capabilities while maintaining balance across modalities. Section: Supervised Fine-Tuning. In this section, we describe our approach to supervised fine-tuning, SFT. Our model is thoroughly fine-tuned using 16 different tasks and 34 varied open-source datasets. We utilize the same chat template for SFT as we did for Yi6B chat, focusing only on supervising the assistant's responses. For more details on hyperparameters and prompt templates, we direct the reader to the appendix. Next, we present our quantitative evaluation results across different areas: image-related tasks, speech-related tasks, and video-related tasks. Since there are limited benchmarks for some advanced capabilities of any-to-any multimodal large language models, LLMs, we also include several qualitative demonstrations to showcase these abilities. Additional details, including decoding hyperparameters and prompt templates, can be found in the appendix. For image-related tasks, we assess our models against others like MIO, Seed Llama, and AnyGPT. We evaluate performance in various tasks, such as image captioning using the MS-COCO-Karpathy test split, visual question answering benchmarks, and a comprehensive visual question answering benchmark called SeedBench. Our MIO Instruct ranks among the top models, showing strong image understanding performance. Although Seed Llama scores higher, our model also supports speech tasks and outperforms larger models like EMU14B and IDEFICS80B, despite having around 7 billion parameters. In terms of image generation, we compare our models with EMU, Seed Llama, and AnyGPT using benchmarks like MS-COCO and Flickr 30K. We measure image generation quality using a metric that evaluates how similar generated images are to real images. Both our pre-trained and instruction-tuned models demonstrate competitive image generation capabilities. Additionally, our model can generate multiple images, such as visual stories and sequences. For speech-related tasks, we evaluate our model's understanding and generation abilities using automatic speech recognition, ASR, and text-to-speech, TTS, tasks. We compare our results with baselines like Wave2 Vec 2.0 and Whisper for ASR, and Vol-E and USLM for TTS. We use the Libri speech dataset for ASR and follow AnyGPT's approach for TTS. We calculate the word error rate by comparing generated transcriptions to the correct ones. Our models perform comparably to speech-specific baselines and outperform AnyGPT. Unlike AnyGPT, which requires an additional model for voice cloning, our models generate both content and timbre tokens, making TTS tasks more complex. Nevertheless, after instruction tuning, we achieve better TTS performance. Section Summary. In this section, we detail our model's supervised fine-tuning across 16 tasks and 34 datasets, demonstrating competitive performance in image understanding and generation, as well as speech tasks, where our model outperforms several larger baselines while effectively generating both content and timbre tokens for TTS. We also provide qualitative demonstrations of our model's advanced multimodal capabilities, addressing the lack of benchmarks in this area. Section: Video-related tasks. In this section, we compare our model, MIO, with other models like Flamingo, Blip2, Instruct Blip, EMU, and Seed Llama for video understanding. We evaluate these models using the MSVDQA and MSRVTTQA datasets, and our results, shown in a table, indicate that our model outperforms all the others. Since there are no benchmarks for generating video sequences in our context, we provide examples of video generation in another section. These findings highlight our model's strong performance in both understanding and generating videos. Regarding multimodal large language models, MLLMs, we note that they are typically built on a pre-trained language model and can understand various types of data. These models align image representations from visual encoders with text embeddings, taking advantage of the foundational model's strengths. For instance, Blip2 extracts features from images using clipvit and then compresses these features to align them with language model embeddings. In contrast, LLAVA connects the image encoder to the language model using a simpler method. These models excel in tasks like visual question answering and common sense reasoning, and some, like LLASM and intern video, focus on understanding speech and video. Recently, there has been a push to unify multiple modalities within a single MLLM. For example, ImageBind creates encoders for various data types, while OmniBind aligns encoders across audio, language, images, and 3D objects. However, many of these models prioritize understanding over generation. To facilitate multimodal generation in MLLMs, one approach is to use external tools like Stable Diffusion or text-to-speech systems. However, as noted in the Gemini technical report, relying on a natural language interface can limit a model's ability to generate images directly. If a model cannot produce images natively, it struggles with prompts that mix text and images. This aligns with our distinction between descriptive and context-aware image generation. Consequently, recent efforts focus on integrating multimodal understanding and generation within a single model, allowing for the generation of multimodal tokens without needing natural language as an intermediary. Different models adopt various strategies for representing images in input and output. For example, the discrete in discrete out (DIDO) method is used in models like Seed Llama, while continuous in discrete out (CIDO) methods appear in models like DaVinci and Gemini. The continuous in continuous out (CICO) approach is seen in models like EMU and MINIGPT5. Additionally, some models combine autoregression and diffusion techniques. However, these models face challenges. For instance, Dream LLM and CIDO models struggle with inconsistencies between input and output forms, making it hard to generate interleaved multimodal sequences. EMU2 encounters issues with the mean square error loss used for training continuous outputs. Transfusion applies noise to input images for multimodal generation but sacrifices some understanding capabilities. To address these challenges, we choose the DIDO approach in our work, despite some information loss from vector quantization. We provide a detailed comparison of our models with other any-to-any MLLMs in a table.